Right, today we've come to to lecture number 12, which concerns portal frames, specifically 3-pin portal frames. Now I'm just going to run through a discussion regarding what constitutes a statically determinate frame and a statically indeterminate or hyperstatic frame. For reading from the notes here, for plane frames, i.e. two-dimensional structures, such as this one here, we know that for equilibrium, the sums in the horizontal and the vertical direction and the sum of the moments around any point must equal 0. We also know that at joints B and C on the frame, any movement in the member AB will result in movement in member BC, as you can see there. If you put a load on there and this column deflects, it actually pushes the beam across to the right. Now, you might think these are just esoteric points, but they are important in structural analysis. I'm just giving you an overall indication here. It's nothing that you have to really remember. But it's important to be able to identify a determinate versus an indeterminate structure. Methods such as moment area, stiffness and flexibility have been developed to analyze structures that are indeterminate, like this one is, using the equations of statics and equations derived from geometric properties such as compatibility. However, all we're going to do today is we're going to look at determinate structures. These notes are an extract from your recommended textbook by P.S. Smith. I've taken a few pages out of there just to get us up to speed, but they will be in your textbooks. For any structure, we will know the geometry and the applied load. Since the load is known, we will be able to derive a set of 3 equations based on the equation of statics for each joint to determine the vertical and horizontal forces along with the moments. Now, I want you people to read all these notes up, because remember that this part of your course is an assignment, and I don't want to spoon feed you too much. I expect you to actually do a bit of work yourselves. So you'll be able to read up on this. But as I've said, this very first page here is not that critical, but it gives you, it educates you, so to speak. They're the forces on a portal frame, and we don't know what the moments and forces in this column are, or in that beam or there, but we do know what they are at the connections there and there. And we're going to do a simple test to see if we can determine whether a structure is statically determinate or not. This is a standard test. If it is not statically determinate, we will not be able to solve it using the methods discussed today. Then we will need to develop further more advanced techniques, i.e. more mathematical methods or using software, which is the go-to system today. We should also remember that the number of reactant forces will depend on the types of support used as shown below. Now, this is a fully fixed support. It has 3 reactants. It has a force there, a vertical force, and it has a moment that can be generated. This is a simple support, as we illustrate on the ends of your simply supported beams. And it has 2 reactions. It has a horizontal reaction because of shortening of this member possibly, and a vertical reaction to hold it in position. This is a roller support, where the only reaction is a vertical one, because the roller can actually move up and down with the change in length of this particular member. Now, there's a standard equation for working out what the degree of indeterminacy is. What we need in 3-pin portals is 0 indeterminacy. So in other words, we want determinate frames. But this is the formula. The number of members, M, plus The number of rigid joints. What is a rigid joint? A rigid joint will be this stiff joint that connects that there. The roller releases, these are roller supports, and the number of joints other than at the supports. So we're going to just run a quick test on a frame. And looking at the frame that we looked at the beginning of this chapter, this frame here, we've got the number of members, 1, 2, 3. There they are. Number of members, 3. The number of rigid joints, 4. 1, 2, 3, 4 rigid joints. The number of roller releases, nothing. There are no roller releases on this portal frame. Minus twice the number of joints. And we look at the number of joints, but we neglect the joints at the actual footings at the base. So there are 2 joints there. And if you plug in what I've just said to you and you put those into this equation, you will get to the point of finding that this portal frame is 3 degrees indeterminate. Not easily solved by normal, you cannot solve it by normal simple statics. You need to do have a more mathematical solution to that. You don't, that's purely academic interest at this stage of your career, because you're not going to do any indeterminate frames. You might do if you go on and study structures to a higher level. So we've got a 3-pin frame supporting a single vertical point load over here. And I'll just run through it, but I will show you a method in the tutorial today that I think is a little bit quicker, probably not as comprehensive as it is in the textbook. The 3-pin portal shown below is supported at points A and F. There the 2 supports are, pin joints there, on pin joints, and has an internal pin at joint C. So if you ran that test, that formula that I've just given you on this, you'd find that it's not indeterminate at all. It is a determinate structure. The frame is loaded with a single point load at point D, over there, vertical point load. Determine the reactions at the supports A and F. In other words, you want to find VA, HA, VF, and HF. That's what we are going to do now. In doing these problems, the ordinates we use, an arrow going up for the y ordinate is a positive, and to the right is a positive x. Going in the other direction, they are minus. So you've got minus x going to the left and minus y going down, and you'll see how important that is as we go on. We're going to now calculate the reactions for the frame. So what we do, and as has been said over here, we make some assumptions. We assume the directions of these support loads, and sometimes they're wrong. We will then, when we solve the equation, we'll find that we get a negative, which will prove that the direction that we chose was the wrong direction. In our example, this example here, in order to ensure equilibrium of the structure, we assume the horizontal forces act in opposite inwards directions. So we've got HF going that way, HA going that way, and we've got VA going up as well as VF. That's what we're saying there. From observation, we also note that for horizontal equilibrium, they must be equal in value. And you saw that with lecture number 11, where we looked at arches. The horizontal forces were always equal to ensure equilibrium. And the same thing occurs with portal frames like this. Though some of them might be minuses and some of them are pluses, as you will see. So we'll now calculate the reactions for the frame. The summation of the horizontal forces in the x direction, HA minus HF, HA minus HF, because they're acting in opposite directions, according to those ordinates, equals 0. They have to equal 0, because the sum of them is 0, and so therefore they equal each other. HA equals HF. The summation of the vertical forces acting in a vertical direction, essentially what we're going to be saying there is that this vertical force going up there plus that vertical force going up there must equal, some of them must equal the load going down of 20 kilonewtons. And so this is what we do. The sum of the forces in the vertical direction, Fy, VA plus VF, VA plus VF minus 20 equals 0. And we can rewrite this equation to VA plus VF equals 20 kilonewtons. We call that equation 2. So, moving on. Taking moments about support A, we're going to take moments about support A for the whole arch. We're going to take moments about there, support A. And with your lecture notes, you'll have a hard copy next to you, I trust. We have VA times 0 meters, because we're taking moments at VA, so there's no distance. Plus HA times 0 meters, because HA also acts at A. So that's why they have no distance, and ultimately they are 0. Plus 20 kilonewtons times 6 meters. I'll just elaborate on that. 20 kilonewtons times 6 meters, that's the distance to this A. 20 times 6 going in a clockwise direction. Minus VF times 8 meters, because that's what that adds up to, VF times 8. Minus HF times 0, because HF passes right through A at no distance. From that, we garner this equation, 120 minus 8 VF equals 0, equation 3. And we can solve this because we've only got one unknown. So VF equals 15 kilonewtons. And we can now form a fourth equation by taking moments about the internal pin C. We take moments about the left-hand side of the pin, as this is the easiest to resolve. We're going to take moments to the left-hand side of this pin. Okay, so to set up an equation, VA times 4 meters is the distance to the pin at the center at C, minus HA times 5 meters, and HA is 5 meters from the pin at C. Simplify the equation and you get equation 4. 4 VA equals 5 HA. We now have 4 equations which we've put together. 1, 2, 3, and 4. And we've just been through those. Now, substituting equation 3 into 2, this one there, which was VF equals 15, we put 15 kilonewtons in there for VF. And we find that VA is 5 kilonewtons, and so forth. You should be quite, having done mathematics and so forth, this should be quite simple for you. But from that we find out what VA is, HA and HF. And the final values for the reactions are shown in this diagram. HA, 4 kilonewtons. VA, 5 kilonewtons, HF, 4 kilonewtons, and VF, 15 kilonewtons. So that's what we've done there. Now, it doesn't end there, because you get situations like this where you get horizontal and vertical loads, and they're a little bit more complicated, but not much more complicated. And just to reiterate what I said earlier, this is an assignment, and I expect you people to research this and to learn how to do some of these things yourselves, though I'm going to spoil you, and in your tutorial today, you'll actually get a lot of information. So, but you can study these. There we have a frame with a vertical load and a vertical uniformly distributed load, including a point load up at D running in a horizontal direction. The method is exactly the same, the methodology. I want you to study this yourselves. And if you go through it carefully, this fellow explains it beautifully, actually. It's one of the best textbooks on the subject that I've found. We have axial thrust diagrams, which is what we're going to talk about. We've already learned how to draw both shear force and bending moment diagrams for beams, and you guys have done that. And we apply similar methods for these 3-pin portal frames. So the analysis of 3-pin portal frames, we calculate the reactions at the supports, which I've briefly shown you today. We then draw the axial thrust diagram, we draw the shear force diagram, and we draw the bending moment diagram. So we're going to find the positions of the maximum bending moment, and note that at that point, just like in beams, the shear force passes through 0 at the point of maximum bending moment, just the same as in the beam analysis I've shown you previously. We will initially calculate shear force bending moment at specific points in the frame. However, as you become more proficient with this analysis technique, it may be possible to reduce calculation time by selecting key points in the structure. And as you become more experienced structural designers, you'll find out what the important parts are. Now we have a frame like this, very similar to the one that you've got in your for your assignment. So I really don't want to do it for you, but you can have a look at it yourselves. The workbooks, work out the reactions. You could then draw the axial thrust diagram, and I'm going to take you through that later in the tutorial, showing you exactly how you work out these axial thrusts. What these are, actually what this says is that this column there has got a compressive force on it of 7.667 kilonewtons, which is actually equivalent to support A. Okay? Sorry, a tensile, it's negative. If you look back at support A, in this particular case, once it's been calculated, you'll see that it's actually acting down. And that's one of the things that you'll have to get used to on these. This horizontal force trying to push this whole portal frame over tends to lift this column up. And this force on the beam there is pushing this down. So you could see that you've got a 19.667 kilonewton force acting upwards, a 7.667 kilonewton force counteracting that by hanging onto the portal frame and pulling it down. But please note that if you add these algebraically, and you had that as a positive and that as a negative, and you subtracted them from each other, they would equal the 12 kilonewton load, so that you have vertical equilibrium. And if you looked at the horizontal forces, you've got two forces going to the left, 10.25 and 21.75 kilonewtons, which is 32 kilonewtons, and you've got 4 kilonewtons a meter times 8 meters, so you've got 32 kilonewtons total pushing to the right, and if you add that to that, you've got 32 kilonewtons pushing to the left. So just as in our arches, in that very first portal I showed you, all these forces must be in equilibrium with the external applied forces. Very important. There the axial thrust diagram is. I'll show you a simple, quicker way of doing it today, but you can please go through this and learn how to do it in the classical way. Over here he goes looking at the shear force and bending moment at each point. So I expect you to study this work over here. All of these, he does it in great detail, and it is self-explanatory. So for senior students like yourselves, you don't have to have a detailed explanation on this. And I think we'll leave it at that and move on to the tutorial now. Thank you.